Yeah, welcome all of you to our presentation discussion about Planetary Sunshade. So I've been working since 2 years now on this topic when we asked ourselves the question, what could space technology do against climate warming? And after some brainstormings, we found actually this idea, which already, I think is already 30 or 40 years old, going back to initial NASA studies. But then, of course, the question was how you could really make it and how you can do it with today's technology and what is possible in today, what is possible in 5 or 10 or 20 years. And on that traveling and finding and research contacts, I found Ross actually at the IAC conference where he made a presentation about this planetary sunshade concept. And since then, yeah, we are trying to extend our research network worldwide. So today it's mainly Europe and US. But of course, we are open to everyone who wants to contribute. As it is, climate warming is a global issue, and we need to react globally. And today, we will see some results of the research that we have done recently. And yeah, I think the floor is yours, Ross, to start with the presentation.
Thank you, Uwe. Thanks everybody for being here. It's always a pleasure to speak to new people about this concept. We've been working on this also for about 2 years. Our endeavors came out of the Space Resources program at the Colorado School of Mines. And we are forming a new organization, the Planetary Sunshade Foundation, to sort of take action towards getting the sunshade feasibility extended and seeing if we might be able to build this. So this is an early step towards building an expert community and presenting the research we've been working on and trying to move out into the broader world. So the agenda for today is in a few parts. First, we're going to discuss the context of the climate crisis and possible interventions, and then go into what a planetary sunshade is. It's a new concept, and we have sort of a working definition of it. It's not a particularly new concept, but the working definition we have is a little more precise. We're going to then sort of make the case for the feasibility of building a planetary sunshade with the mineral resources of space in this century with technology currently on the horizon. And then we're going to move on to current research going on at Airbus, University of Stuttgart, and the Colorado School of Mines. And we aim to have that presentation last about an hour, and then we'll take the second hour for open discussion. The presentation will be recorded and we'll be posting it on the planetarysunshade.org website. And the discussion we will leave unrecorded and just take notes. So the framing context of all this is our carbon emissions and where are the climate tipping points. The graph here is sort of our climate futures that we may be looking at. The IPCC warns us that we are rapidly foreclosing on the possibility of a 1.5 degree climate future, and that the opportunity to limit climate change to 2 degrees will require dramatic action. And the current policies and the pledges and targets we're at are in a 2.5 to above 3 degree world. So what does that mean? Well, 1.5 degrees is considered safe. 2 degrees risks catastrophic tipping points. If we're on track for 3 degrees, that might be an emergency. So the question we're asking is, do we need to cool the planet? Besides reducing emissions, which is absolutely critical and cannot be accelerated fast enough, is that going to go slowly enough that we will have to take emergency intervention? So here's sort of the current state of climate intervention research. The National Academies just released a report last week recommending $100 to $200 million in US federal funding for research on reflecting sunlight into outer space. They only considered atmospheric interventions, and we believe that space interventions like the planetary sunshade should be a part of the conversation. Right now, the EU-funded GENIE study is taking a broader inventory of other sorts of climate interventions, and we're fortunate to be in conversation with the researchers on that study and sort of shaping our ideas about the planetary sunshade to be able to inject into the social science and policy discussion. So that's the sort of overall context for what we're working with right now. We need to be mindful of the magnitude of what we're talking about and the consequence of these decisions. So the climate intervention decision is of an enormous consequence. It will affect every living thing on Earth, whether we do it or not, because if we create a climate catastrophe, inaction is also a choice. So if we decide to not do anything, we might be accepting mass extinction, widespread suffering, and an irreversibly changed planet. If we decide yes, we might stabilize the climate, buy time for carbon removal, which is the only permanent solution, and preserve an environment which is literally irreplaceable. We cannot fix it if we destroy it. It does not solve everything. It does not address ocean acidification. It can only approximate a pre-industrial climate. Small interventions with less CO2e in the atmosphere are going to be better with less side effects than larger interventions. And so I really want to underscore that we need to be mindful of the hard and the soft risks in contemplating climate intervention. The hard risks are technical risks. The strongest example of a technical risk is termination shock. That is, if you cool the climate and then abruptly stop cooling the climate, the climate snapback warming will be worse than if you had never taken intervention in the first place. So you have to be sure that you're not going to end up like that. Soft risks are less amenable to analysis. They are political. This is high stakes politics. Climate politics have always been high stakes. It's going to get more high stakes. There's going to be unpredictable outcomes. Even research needs to be sensitive of taboo. This has been a strong taboo, which is lifting, as evidenced by the National Academy's report and the Genie study. But we still need to be very careful of people's fears of changing nature and respect their desire to live in a pre-industrial world. And because this affects everyone, we need to consider the views of those who agree and who disagree with us. But all that said, it is time to be having this conversation. And if things continue to go as they are, in 10 or 20 years, a set of world-changing decisions could very well be made, and space-based technologies could be a very important option. So first, I want to address the objections to research, because this is something that comes up in the popular conversation. It's a very polarizing topic, and we need to be prepared for it. So many people have strong objections to any sort of even research in this topic. It is clear that international consensus should be developed prior to intervening, but even experiments are controversial. You may have heard about Harvard's ScopeX experiment in the news. This is a picture of it on the right. It's designed to release a kilogram of chalk and measure its dispersal in the atmosphere, in the stratosphere. It is an objectively harmless study. It provides information that is very important, but there is strong political opposition to it, and they are still working on trying to get permission to fly. And this is how it is, because climate intervention is inherently political. So the arguments that we need to be aware of that are going to be deployed against even thinking about this topic is first the moral hazard argument. It's rooted in a fear that climate intervention will be used as an excuse to limit CO2. That's not what we're rooting for. That's not at all what we advocate, but it's a valid fear because people can argue for the status quo using whatever is around. The other argument is a slippery slope argument. That is, if we start doing this, we won't be able to stop and we'll be committed to it. I think the planetary sunshade is such a challenging and hard thing to build that it is sort of less likely to come to a slippery slope, but we will have to face that. So our goals in terms of policy, which we need to start alongside technical research, are to establish a governance and policy group, define checkpoints and off-ramps for how we proceed with this research in a way that's responsible to all of humanity. Okay, let's dive into the technology. So the technologies for reflecting in sunlight into space are solar radiation management. And they can be split into atmospheric technologies and our space-based technology. So starting at the surface, marine cloud brightening can cause local cooling. It's sort of emulating what happens with bunker fuel ships that cause clouds over the ocean. This creates a local cooling effect, and it can be used to stabilize coral reefs and other sensitive ecosystems, but it cannot create a global effect. And so it's not a global solution. In the upper troposphere, cirrus cloud thinning may work. That's also advocated for funding with the National Academy study. It's based on removing a blanket rather than increasing reflectivity. Needs more research. The main SRM technology that we're going to be operating in comparison to is stratospheric aerosol injection. It is up above 16,000 meters. And it's the best understood technology, understood well through volcanic eruptions. Mount Pinatubo, for instance, released 15 to 20 megatons of sulfur dioxide. This formed long-lived reflective clouds in the stratosphere and cooled Earth by 0.5 degree for 2 years. So injecting similar quantities of aerosol with aircraft could have a similar effect. And at the top here, we have the planetary sunshade. So if you look at that picture of the sun, there are 6 dots in front of it that block about 0.5% of the sunlight, and this cools Earth by about 1 degree. So the advantages of this are that you can interact with the climate system from outside the environment. You're not altering atmospheric chemistry. It is a durable, lasting a century or more, so you don't have to continually replenish it, and it minimizes environmental disruption. So all of these solar radiation SRM technologies should be seen as complementary, even if they're not deployed. A portfolio of technologies reduces the risk of termination shock. For instance, a planetary sunshade could provide an off-ramp from sustained stratospheric aerosol injection, and stratospheric aerosol injection could provide a fallback in case a planetary sunshade could not be maintained for a century or more. So more on where the sunshade fits within the climate intervention technology portfolio. A sunshade is slow, expensive, and clean, whereas atmospheric techniques are fast, cheap, and dirty. A sunshade scales up very slowly, but can scale down very quickly because it's controllable. It provides an off-ramp to other technologies. Importantly, it can shade the poles preferentially, which is something very critical for approximating a pre-industrial climate. Spectrally selective sunshades could minimize interference to precipitation patterns throughout the globe. It could, if built correctly, send power back to Earth by microwaves, providing enough power to accelerate CO2 removal across the globe and work towards a permanent solution. And it also provides positive externalities for space development. So here is the sort of brief history of the sunshade concept. It was first proposed by James Early in 1989. That paper identified the principles of how a planetary sunshade would work and identified that lunar resources should be used to build it. Interestingly, that was only 1 year after James Hansen testified to the US Senate about the existence of climate change. So it's a quite apparent idea, really challenging more in its scale than conceptually. Several other papers came out sort of riffing on that. The next major development was Roger Angell in 2006 proposed a swarm architecture launched from Earth, not built with space resources. That involved a rather ambitious sort of coil gun-based architecture shooting through the atmosphere. But it did come up with a minimum mass solution and was rather high-tech and innovative. Kennedy et al. In 2012 proposed a Dyson dot architecture, which was a first that we're aware of a photovoltaic sunshade that beamed power back to Earth, produces enough power generally to sustain civilization, quite a fantastic amount of power. Sanchez and McInnes in 2015, Colin McInnes had been working on the sunshade since about 2002 off and on, but 2015 was the sort of the culmination of this work that proposed a control law and modeled the climate effect of the sunshade, and we're going to briefly review that result. Ourselves at Planetary Sunshade Foundation and Colorado School of Mines incorporated Starship into the architecture and started proposing that we actually build a planetary sunshade in 2020 at IAC. And right now in development, we have Uwe Brouwer at Airbus, who is developing the IPSS, International Planetary Solar Shield concept. And Sebastian Fix and Tarshan Maheswaran, who you're also going to hear from later, have done their master's theses on the IPSS concept. And Liz Scott in the audience is starting her dissertation at the Colorado School of Mines on resource logistics. And there's a bibliography courtesy of Yomi Shayer at Harvard, posted on our website for more information. So here's sort of the fundamentals of what a planetary sunshade is, kind of our working definition. It's different from other space-based concepts that you might have come across, like creating a giant dust cloud or putting mirrors in low Earth orbit. And the quantities here are generally a rough order of magnitude to account for a range of assumptions and free variables. So first off, about a planetary sunshade, it's crucial to note that a planetary sunshade remains relatively stationary between the Earth and the Sun, and that means it has to be parked at Sun-Earth Lagrange 1. That's a gravitationally stable balance point, about 1.5 million kilometers from Earth. That's 4 times farther than the Moon and 1% of the way from the Sun, to the Sun, excuse me. And it's the only location in space where an object can remain in front of the sun as seen from Earth. It's important to note that although it's very far away, it is energetically quite close to the moon and to near-Earth asteroids. And while it's stable, it requires a constant station-keeping thrust for orbital control, just a very small thrust. And the propellant required for that would add up over time and be infeasible. So the way a planetary sunshade keeps station is by solar sailing. That's a fundamental principle of it. It's controlled, and it surfs off of a very gentle push from sunlight, like a wind against a sail. So the sunshade then has to be a thin, flat structure that can control its orientation like a sail. You can do that by altering the reflectivity of its different corners and using that to tack against the against the sunlight. It's important to note that if control were to fail, it would be pushed off course in about a year. So the sunshade needs to be maintained. It doesn't physically degrade very much in the space atmosphere. There'll be some radiation damage, some micrometeorite damage. There'll be a maintenance involved. But on the whole, the sunshade should be expected to last for a century or more, as long as you care to keep it going. Interestingly, and perhaps counterintuitively, unless you're an orbital dynamics person or you play Kerbal Space Program, the force of sunlight pulls the effective SEL1 stability point closer to the sun rather than pushing the sunshade closer to Earth. So lighter sunshades are pulled away farther from Earth, and thus they need to be larger. So although mass is generally the enemy in space architecture, heavier sunshades are more area efficient. The area required is very large. To block 0.5% of sunlight and get 1 degree cooling, it needs to be about 1 million square kilometers, which is about the size of Egypt. That sounds incredible. It is incredible. We've obviously never built something that large, but it is also equivalent to about 20 years of terrestrial aluminum foil construction. We build a lot of thin films on this planet. We just sort of dispose of them and don't assemble them in space. It does not need to be a monolithic 1 million square kilometer system. It can be broken up into smaller units, and it should be broken up into smaller units. The total size is what matters. So the mass is going to be on the order of 100 megatons. For scale, that's about 3 years output from Earth's largest iron mine. And there are a range of various architectures from down to maybe 10 megatons at the most fantastically light to a gigaton plus, just sort of built heavy and providing power to the Earth. It's important to note that mass is not the only thing to optimize here. We are going to need to build new paradigms for operating in space. And that's going to mean taking advantage of the mineral resources in space at scale and not launching this stuff from Earth. And one of the main points of this presentation is I'm going to show that it's going to be possible to bootstrap the technology, the capabilities we need using the technology that's already in development. So it should definitely not be launched from Earth. It should be built with space resources. The hardest thing about space is launch from Earth. When launching mass into space, gravity is the enemy. The Earth is so heavy that space travel is almost physically impossible. It's just trying to get off Earth has been a bottleneck that has made access to what should be a very easy to work in environment very, very hard. So we're relying on a space launch revolution to be able to increase our access to that environment, but we do not advocate launching 100 megatons of mass off of Earth. There are abundant resources in space. They're not necessarily better than Earth materials. They're just basic industrial materials, but they are abundant. Aluminum, silicon, iron, oxygen, water, it's all there for the taking. In fact, there's enough resources in the inner solar system to sustain 1 trillion people. So a photovoltaic sunshade also, as a final point, could make as much power as civilization needs. You could do about 70 terawatts in the photovoltaic IPSS architecture, which is about 5 times more than the total energy supply required by humankind right now, and is expected to be about what we need in mid-century, when the vast majority of the world's population will be living an industrial lifestyle. This energy can be transmitted to Earth via via microwave, and it can be used to remove CO2. The reason we're advocating using that energy to remove CO2 is one, because we're focused on the climate crisis, but also because the risk of termination shock is real as well. If you lose your planetary sunshade, you do not want to lose all the energy that would be required to sustain day-to-day life. So it seems appropriate to use that energy to a long-term, century-long project of removing CO2. So here is the predicted climate response of a planetary sunshade. This is from Sanchez and McInnes 2015. Upper left picture shows displacement in the z-axis, normal to the ecliptic, showing July in the middle of the figure, the Arctic summer, preferential shading on the poles, and in the Antarctic summer, preferential shading on the South Pole. The bottom left shows the predicted temperature response for a rather catastrophic 2x CO2 world. And it shows that relative to pre-industrial temperatures, Earth's temperature can be held within about a degree of that, importantly keeping the poles within about a degree of pre-industrial temperature. So on a purely thermal basis, it's probably sufficient to stop the loss of ice caps and stop the loss of, stop widespread heating. It's important to know that this makes no predictions about precipitation patterns. And if you take a 560 ppm carbon world and you bring that down to pre-industrial temperatures, you're going to have dramatically altered rainfall, and you're going to have quite a bit of change in ocean acidification. So not a silver bullet, but it could be a very important part of the solution. Okay, so here is my pitch on how you build a planetary sunshade. And the short answer on how you build a planetary sunshade is you build a space resource economy. And once you build a space resource economy, building a planetary sunshade is a matter of scale. So it rests on 3 planks: space resources, resource logistics, and in-space construction. The overall sort of roadmap consists of several mission phases. This is the roadmap for the IPSS architecture being worked on in Germany. Sort of in phase 1, the initial technology requirement is to derive a baseline sunshade architecture towards technology maturation and have that represent feasible sunshade concepts, and then to develop a resource and logistics model to support the construction based on the nearest term feasible technology. To identify the technology gaps, rank them by severity, update and refine the model on a continual basis, and sort of the exit criterion from this technology development phase, which is to have a high fidelity model with no gaps, to understand what it is that we're intending to build. And we think we have until about 2035 to do that. At that point, we expect to have a revolution in space launch capability and a base on the moon. Alongside that technology development phase, there are science goals. We need to incorporate the baseline architecture into a digital twin of the Earth's climate. We need to understand the heliophysics effects on large structures at SEL1. We need to acquire detailed resource maps of the moon and near Earth asteroids and integrate all that. The exit criterion on the science will be a confident understanding of the sunshade's effect on climate, the sunshade operating dynamics, and resource economics. And then policy is an important plank also in this roadmap strategy. In the first phase, we need to bring together an expert community. We need to establish a policy and governance group, and we need to develop information resources for policymakers and draft a policy for sunshade development towards the end. The exit criterion for the policy, which is moving towards demonstration, would be international political license for sunshade development, whatever that might look like. It is a political question that we have to begin to engage with now. Stage 2, after exiting stage 1, would be to engage in sunshade development and construction. This consists of demonstration and also production and ramp up in the IPSS model here. So the technology goals for stage 2 and 3 here are to develop sunshade prototypes with lunar resources, to scale the space resource architecture to climate relevant scale. That's going to be the ability to extract and utilize about 100 megatons of material from the moon or asteroids, establish the resource logistics and in-space sunshade construction facilities. And then on the science policy, we're going to have to monitor the climate response as sunshade construction occurs. And politically, we're going to have to continue to report to a governance structure, which is found on the development efforts, and conduct that development in accordance with international agreement. The exit criterion from this sort of long phase that we think might be able to be achievable by 2060 would be a sunshade that is complete and operational, meeting our climate goals and providing power to remove carbon from the atmosphere. Continuing operations are going to require maintaining the sunshade and scaling it as required by the policy, developing the ancillary benefits, probably building out more energy supply, in-space construction, other things that are hard to foresee, continuing to monitor the sunshade's effect, and continuing to operate in accordance with the international agreement. At some point, and we think this might be maybe 2200, the exit criterion from the operations phase will be that the sunshade is no longer needed for climate stabilization, and you can move into decommissioning. At decommissioning, because it's a solar sail, you can execute a controlled departure from the Earth-Sun axis, and you can redeploy it where it's desired. It could be an industrial site in the asteroid belt. You could use it to terraform Venus, or you could recycle it into other things. That's exciting options for future generations. So how do we get started on this? And the answer is we're already getting started. So this is an exciting mission. It's a light sail mission to SEL-1 called NASA's Solar Cruiser. It's sort of a successor to the Planetary Society's Light Sail 2 mission. It's not a planetary sunshade, but it flies like one, and it flies where a planetary sunshade flies. So it's a rather large solar sail for Earth launch. It's about 18,000 square meters. And it's going to be deployed into cislunar space and use solar sailing to maneuver to SEL-1 and to demonstrate orbital control around SEL-1, which is the same sort of dynamics that we're going to need to control a sunshade on a larger scale, and then to move around from there. So this is sort of an exemplar of quite a bit of technology that's going on right now with this new vision for space exploration. And the sunshade was really inspired by pulling together what's going on here. And so it's really a question of taking what's going on, integrating it, and then scaling it up if we decide to go forward. This is another concept from Airbus on a factory in space. So this shows building a rather large structure from materials in space. And this is important because you just can't launch arbitrarily large materials from Earth. You have to get it into a rocket fairing, and it has to take this very high stress, high G, high vibration environment, which is much harder than just standing in 1G, and then you have to deploy it into 0G. So it's, again, like launching from Earth is hard. So it's much better to construct in space. But again, we're looking at 100 megatons of material, and that's going to take probably more than you're going to be able to launch from Earth. So the question is, how do you get the raw materials to scale? It's important to note that this is not necessarily a new concept. In the 1970s, Jerry O'Neill and his students envisioned giant free-floating space habitats built from lunar materials. They had plausible architectures to build them. The problem is it didn't work out because the space shuttle, which they were depending on, needed to be more than it was. So we're hoping to have another chance to have access to space that's revolutionary. We're hoping on new launch architectures like Starship, like New Glenn, like other launchers, but Starship is sort of our baseline. And so the planetary sunshade kind of rhymes with the O'Neillian dream, and the capacities that we need to build it are the same capacities that they needed. And it's also important to note that if you can build a planetary sunshade, you can also build just about anything else in space. So these capabilities have an incredible value, whether or not a sunshade becomes necessary. But planetary sunshade research might drive these capabilities to need to scale faster. So this is some current efforts on learning to work with space resources. On the left, we have NASA's Viper mission, which is going to go to the lunar poles, explore water resources and other mineral resources, and provide information useful for siting an Artemis base, probably useful for siting the Moon Village, other sorts of activities that are going to take place at the poles. On the right, we have the ESA Space Resource Roadmap. So this is an integrated vision for using mineral resources of the Moon and asteroids and also Mars for various applications. The sunshade just sort of rides along with this, and eventually, if you decide to scale it up, it just sort of redirects it. So I just want to be straightforward in the next few slides about sort of like what kind of access to space we're talking about. We're going to need a revolution in space access to make the sunshade feasible. 100 megaton structure is 5 orders of magnitude larger than the ISS. It is just out of the question with the 20th century approach. And that's why people haven't really seriously proposed building the sunshade yet. But we think it's possible. We think the fastest possible path to the capacity we need is to be free riders on SpaceX's plan to build a city on Mars. Building a planetary sunshade is on the same order of scale as building a city on Mars. And it's really critical to note that this is a complementary endeavor. It is not at all competitive, but instead they feed off of each other very strongly. So sorry about the small print and sorry about these tweets. It is 2021 though, and that's policy. These tweets make the case. Up at the top, SpaceX is going to build 1,000 starships. That is what they are existentially dedicated to doing it. That's why they don't mind crashing so many prototypes. That's why they're building with stainless steel. And that's why they're launching their Starlink constellation, which is going to bring them about $30 billion a year in revenue to do this. However, with these 1,000 starships, the Mars launch opportunities occur only every 2 years. So that is an incredible amount of idle launch capacity. What are they going to do with all of these starships between Mars launch seasons, right? This is why I propose we can be free riders on their plan. SpaceX's Starfleet will be sized to deliver a megaton of infrastructure to Mars. A megaton of infrastructure is about what we think also you need to build a Sunshade infrastructure on the moon to get 100 megatons of resources off the moon. That 100-to-1 mass leverage is critically important. And it's also critically important that access to the moon is about 50 times faster than an access to the Mars. You can get to the moon and back in 2 weeks. Mars mission takes you 2 years. So it looks like if SpaceX can build a city on Mars, then we can build a planetary sunshade in their spare time. A single Starship is intended to launch in a day what the whole world launches in a year. But even so, it's too massive to launch a sunshade from Earth. It would require about 1 million Starship launches that would burn about an order of a gigaton of methane in Earth's atmosphere. So what we need to do is to establish a sustainable resource economy in space. And that requires a lot of thinking and not just a brute force lift. So here's what a sustainable resource economy in space looks like. And I'm pretty upfront here by just showing a bucket wheel excavator. This is an accurate description of the technology that we'd be using. Lunar regolith is a rich source of aluminum and silicon, two of the primary materials out of which a sunshade could be built. This base material is everywhere. It doesn't require any luck to find it. And you also can get iron, and in extracting metals, importantly, you get abundant oxygen for free. This oxygen sustains life, and most of the mass of rocket propellant is oxygen, so you partially refuel your return vehicles for free as a byproduct of metals production. There's also water on the moon. It's trapped in deep, permanently shadowed craters. We think it's eminently accessible. There might be a lot of it. We think there might be gigatons of it. It's not as abundant as the metal resources, but the water can provide liquid hydrogen as well, which is very important for other sort of lift launch technologies. The bucket wheel excavator is 19th century technology. It's been studied for use on the moon. It works well in low gravity. It has very few moving parts to be clogged by dust. It's a simple thing that presents low technical risk. Like most industrial equipment, it's heavy and it's dumb and there's not a lot to go wrong with it. An excavator like this masses a few kilotons. It's well within our 1 megaton mass budget. And even so, most of this structure is girders and the like. These girders don't need to be launched from Earth. You can make them from the output of a smaller lunar mine. And bootstrapping like this can really reduce the mass we need to launch from Earth. So the better we can put together our space resource architecture, the less of an environmental footprint we need to have to launch all this mass from Earth, and the more scalable and sustainable our technologies are. So mining and energy, these are the bases of a material economy, right? On Earth, we use mined products every day. If it's not farmed, it's mined. So we usually don't see this, and when we do, we don't think about it, or we think about it negatively, but the foundation of our technological existence is on mining. And I want to acknowledge that there's some people who say that we shouldn't mine the moon because we'll ruin it, just like we did Earth. And it's true that we'll have an impact, but this impact is very small. A few tens of kilometers for a mine site is about 1/1,000,000th the size of the moon. That's about the amount of area we need. And today, we humans use fully half of the Earth for industry or agriculture or cities or towns. So if it comes to using 1/1,000,000th of the moon to save all of Earth, I think there's a strong moral argument to be made for that. I think there's a strong environmental argument to be made for that. And it will require utilizing, several tens of square kilometers of lunar resources. Okay, so to do all this, we're going to need to have humans. We're going to need humans in the lunar environment because machines are part of what we work with, but you can't just do it with robots. Apollo astronauts did more lunar geology in a few days than robots ever have. Machines are meant to work with humans. We use them, we fix them, we do what they can't. Robots are amazing and they're an incredible force multiplier for human endeavor, but getting them working right in new environments without any supervision, they're going to break. They're going to need assistance. There's going to be things they can't do. So humans are force multipliers for robots. Robots are force multipliers for humans. I sort of got a joke. I don't know if everybody else thinks it's funny, but you know what you call a robot that works? It's a machine. We need both. We need a lot of machines and we need a lot of humans. So continuing on that theme is that the technology we need to support a lot of humans is not new. On the left is an Apollo lunar lander, and on the right is a Los Angeles class submarine. These are shown to scale. They were built at the same time in the 1970s. The lunar lander supported a crew of 2 for 3 days on the moon. The USS Los Angeles supported a crew of 129 for 34 years under the sea. Under the sea at 30 atmospheres of salt water is a hostile environment. It's probably more hostile than space in a lot of ways. The submarine can go without resupply for 4 months, taking only oxygen and water from its environment. As I mentioned, there's abundant water and oxygen on the moon for life support. You don't have to have a perfect closed loop, although the closer to closed you get, the better. A single Starship can bring enough food to sustain the crew of this hypothetical submarine moon base for 4 years. So you can feed them. It is amazing that this ship costs about the same as the lunar lander. They both cost about $1.5 billion in today's dollars. So it's really a question of paradigm and how you build it. The way that we did it in the 20th century with space is not the way that we need to do it in the 21st century with space. If you could modularize a submarine and adapt it for the lunar environment, even with no weight savings, SpaceX's Starfleet could deliver it to the moon in less time than it takes to send a cargo ship across the Pacific. So we can support hundreds of people on the moon if we can scale up like this. And scaling is not the obstacle. Okay. Resource logistics. So this is sort of the last question is, you've got all these resources, you've put it together on the moon. How do you get it off into space? There's two options for getting the resources back off. Number one is lunar sourced propellant, which I discussed. We think there's probably about as much water down here at the lunar poles as there is oil in Saudi Arabia. So it's not necessarily a infinite resource, but it is an abundant resource, and there's a strong case to be made for using it to get a planetary sunshade going. The mass fraction of just using rocket launch to get it off the moon, it would be about 1-to-1. It's much easier than launching off Earth, and you also don't need fancy atmospheric class vehicles. You can pretty much just use like a shipping can with a rocket engine. So that's one option for developing infrastructure. And a second option for logistical infrastructure is much more elegant, and you're going to hear about it more from Tarshan at University of Stuttgart, which is to use electromagnetic launch. And this is actually an image left over from the sort of O'Neillian days of the 70s. The idea is you just put a mass driver on the moon. You have a series of magnets that accelerates a slug of raw material up to about 3 kilometers a second, and it shoots it off maybe towards EML2 is a good staging ground for logistics. You might need a little package with a kick stage to get the orbit stabilized when you get up there, but you can take a whole lot less water resources to do that. And it's also much more energy efficient. The electromagnetic launch energy requirements are on the order of 2 gigawatts, which is big, but it's about as much power as one city requires on Earth. In-space manufacturing is it's actually almost the easy part. We're definitely working on how to do that. You're going to hear some work from Sebastian Fix at University of Stuttgart on some concepts for manufacturing the sunshade. But sort of the Planetary Sunshade Foundation's argument is that if you can get the resource logistics in place, then building these thin film structures is eminently doable. Vacuum and microgravity drive scalability. There are many viable commercial and government actors who are developing technology to build large structures in zero-G. It's comparable to assembling 20 years worth of global aluminum foil production into a sheet with a sort of structural base behind it. And then upgrading that to a large photovoltaic array with microwave beaming technology is a matter of scale. It's more complicated, but it's just doing things repetitively and at large scale. So there'll be some more information on that from the University of Stuttgart. And I'd like to introduce the next speakers here. We have Uwe Brouwer at Airbus. He's going to present the International Planetary Sunshield ConOps. We have Liz Scott of Colorado School of Mines, who is developing a quantitative resource roadmap. Sebastian Fix at the University of Stuttgart is developing sunshade construction strategies. And Tarshan Maheswaran is developing a coil gun-based launch system. Thank you. Uwe?
Yeah, just to visualize a little bit what is so to say the concept of operations of such a sun or gigafactories in space. This picture shows how we can really bootstrap and how we can start all the things. So there was a slide from Ross showing the rough schedule. So starting from now up to 2060. This is, of course, just an estimation based on, I would say, some assumption that there is not such high urgency to do something. And as you know, like when there was the mission to moon in the last century, in 7 years you could fly to the moon. No one ever thought about that. So it's a matter of priority. So of course you can speed up things. The other thing is what I wanted to say is if you look at this picture, you will find many elements which are already in the roadmaps of the space agencies. So we tend to reuse what is already in the roadmaps, like having these space trucks for a moon economy, and want to make it um, or extend this concept with the specific things or the specific technologies that we may need for the production of these gigasails in space. And the initial idea for everything will be to work a little bit like SpaceX. So really start doing things and not doing 10 years of analysis, trying to manufacture sails on Earth with, I would say, realistic or representative materials and methods, try them out like SpaceX is doing with the Starships, and see how they behave and what is their, how the material behaves and so on. And in parallel, work on the moon roadmaps and create all these necessary technology elements for in-space resource utilization and for in-space manufacturing and production. So this is just a brief overview just to visualize the different elements. And it's really what Ross was saying, it's a kind of bootstrapping approach. Yeah. So if you have in mind these big mining facilities, you will not send up the big mining facilities from Earth. You will send up some, I would say, avionics, some critical elements, but the structures you will build on the moon in a bootstrapping approach. Because the metal, the material is there, you just need to mine it. And you need to produce it. And you need to use 3D printing, ALM manufacturing, whatever, to create these structures. First, to set up the moon economy, and then using it also prefabricated on the moon or fabricated at Sun Earth Lagrange point 1 to create these gigasails to, in the end, to have this 1 million square kilometer sizing for 1 degree, which is of course also scalable. If we need less, we do only half the sizing and you have half the temperature. If you need more, you do double the sizing. It's a very flexible concept. And the most important thing for me, which I want to stress here again, is we really are doing most of the things out of the Earth biosphere. We have a very low impact of the activities on the biosphere. And as Starship is aiming to use green methane, I think the impact will be lower than any other technology in terms of geoengineering, which I have seen. And it's the less risky method. And our aim is to come to these agency roadmaps and to the politics with a message, let us do the technology development right now, up to 2030, 35. And then we can decide whether we really build a system. It's just a risk mitigation to have a plan B. It's always good to have a plan B. I think this is the message that which I wanted to give. So we can go on.
Thank you. Liz? I think your slide was the next one. Are you muted?
Am I muted? I hope not.
There you are.
Am I good?
You're good.
Okay, thank you. So I guess, one of the points that we really want to make is that
Liz, can you speak a little bit louder?
Oh,
is it possible?
Sorry, can you hear me okay?
Yeah, you're a little quiet, but I can hear you okay.
Okay, I'll yell. So one of the points we want to drive home is that space resource utilization is not a fringe activity. Today's space race is all about learning to stay on these planetary surfaces permanently and going for a sustainable space exploration style. Space launch vehicles will get us there, but we need them to deliver the equipment that lets us use these resources in place. So this includes things like water and oxygen, construction materials, and rocket fuel. These are things that we shouldn't need to bring from Earth, otherwise it's just a camping trip. So the Colorado School of Mines has over 100 graduate students in the Space Resources program, and right now it's the fastest growing program on campus. There are universities, companies, and governments everywhere that are working to develop these technologies right now. So this is a paradigm shift, but it's not rocket science. It's industrial mining technology applied beyond Earth. Rocket science is horribly demanding, and as we mentioned, it's barely physically possible, and it explodes if you do it wrong. But industrial technologies like mining and manufacturing are easy to master and to scale. And given rapid, sustained, and cheaper access to space, working with space resources will become commonplace. And that's what we're waiting on, is this revolution in access to space. Next chart. Excuse me. So the field of space resources is huge, and it's expanding rapidly as space agencies and industries look to move away from the flags and footprints model of space exploration and into more of a long-term sustainable space development. But due to the still high cost of access to space, much of this current work is still theoretical or based on terrestrial testing. There are a lot of different options for use of space resources on a project as big as the Sunshade, and eventually we'll probably end up using them all. But resources such as metals and glasses, water and oxygen could come from locations on the moon or on asteroids. These resources can be extracted, processed, and manufactured into parts and moved around cislunar space in many different ways, each with their own associated costs and energy requirements. So we know that the resources are out there and we're developing the technologies to extract and use them, but what's the best way to go about it? Which resources should we use? Should we look at the moon first, or should we look at asteroids? Which technologies provide the most bootstrapping bang for the buck? What's the best place to put a logistics hub? Would that be in low Earth orbit or in Earth-Moon Lagrange point 1? Humans have never built anything on nearly this large or complex in space before. The biggest thing that we've built in space so far is the International Space Station, which took 20 years to build and can house at most 7 people at a time, and is considered to be the most expensive object ever built. So probably not the best example to follow. So to address some of these questions, my PhD dissertation will attempt to provide a quantitative roadmap to chart a course to developing the environment necessary to build the Sunshade. The goals of my project are to quantitatively assess the economic and technical feasibility of building space megastructures, including the Sunshade, and to produce a roadmap for the most efficient technology development for achieving the cislunar environment necessary for megastructure production. So to build this roadmap, my dissertation will create a quantitative model of cislunar resources and current and near future space technologies. This information will come from the best available sources, and it depends on what we're looking at. So information on in situ resources will come from prospecting and science data, and that will include things like sample return missions from the Apollo missions and Hayabusa to an asteroid. Excuse me. Technology information will come from both academic and industry research and testing, and will be represented in the model as processes, since they essentially convert one resource into another. So for example, a thermal mining rig converts in situ water ice into captured water ice. A 3D printer converts metal feedstock into something like a support girder, and a transport ship converts Earth-made avionics components in low Earth orbit into Earth-made avionics components at Sun-Earth Lagrange point 1. So the model will then step through these time increments to simulate transformations of resources through these technological processes to go from in situ resources all the way through completed megastructures. And by combining different resource, technology, and logistics choices, different stories can be told about the best way to build these megastructures like the Planetary Sunshade. So best in this case could mean cheapest, it could mean the fastest, it could mean the lowest launch mass from Earth. The model will also be able to compare certain scenarios like different Sunshade architectures, so comparing sort of a low-tech, simple thin foil structure to something more complex like a photovoltaic Sunshade. It can compare things like launching from Earth using using a maximal use of space resources. The model is designed to be updated indefinitely, so even past the scope of my dissertation, as new prospecting data is gathered on resources and new technologies are developed. The model will be open source, and it will be available for public use by researchers, policymakers, and industry. So some examples of the technologies that will go into the model are detailed on the next slides.
Sebastian?
Yes, so hello everyone. My name is Sebastian Fix. Can you hear me? Is everything fine?
Sound good.
Okay. So I am one of 3 master students from the University of Stuttgart, performing feasibility studies on the idea of the International Planetary Sunshade. And in our studies, we analyzed the technological feasibility of the Sunshade. So with the information from previous Sunshade studies, we identified key technologies required to manufacture and operate the Sunshades at L1, including resource utilization, Sunshade manufacturing, power generation, and logistical operations. We then analyzed how, with the current state of the art, an appropriate sunshade constellation could be realized in a timely and reliable manner. And you will see that many technologies, when we incorporate it into our concept, are already in development, with demonstrations planned in the near future. So as you heard a couple of times already now, our concept also takes off with the current momentum in the space industry, and the initial development effort for the sunshade specifically would be much smaller than expected. Now, a very important strategic question is how the sunshade should shade the sun. There are different ways to interact with the solar light in order to reduce the radiation reaching the Earth. As you can see on the right, the light could just be reflected back towards the sun. It could be refractively deflected away from the Earth at a small angle, or it could be absorbed by the sunshade and then be re-emitted as infrared radiation. The reflectivity of the sun-facing surface is a very important parameter. High reflectivity also requires a high sunshade mass as an anchor against the solar radiation pressure. In this context, light deflection with a refractive screen would be preferable, since it minimizes the light impulse onto the sunshades. And as you heard, refractive sunshade concepts such as the Roger Angel approach are currently the lowest mass concepts by far. Refractive screens, however, must be manufactured precisely and with geometries in the nanometer range, and with the high production effort required for the sunshade with millions of square kilometers of sunshade surface, simple manufacturing processes that produce reliable and robust components would also be preferable. So in order to reduce the manufacturing complexity for the sake of feasibility and speed, and with the price of increasing the total mass, we think that a thin metal foil should be used as a reflective or a re-emissive screen. So we already heard that the materials from the moon are the optimal starting point for the sunshade production. And on the next slide, we can see that aluminium should be used as the basic foil material for its low density, its good mechanical properties, and high lunar abundancy. And to reduce the reflectivity of the aluminium, a texturing should be applied onto the foil during the production. There are two foil production processes that could be used in space. The first one is rolling an aluminium sheet down to several micrometers of foil, as it is done in terrestrial aluminium foil production. Here, a minimum thickness is reached at about 10 micrometers, which is why this technology would only be applicable if a rather thick foil is sufficient. Evaporation breaks this barrier. Here, a thin film of aluminium is grown atom by atom onto a substrate and then removed from this substrate. And the minimal thickness of the foil is only limited by the required mechanical strength of the foil. Foil rolling is a technology with substantial experience terrestrially, but it has not yet been adapted to the space environment. Evaporation of aluminium foil, on the other hand, has been demonstrated in laboratory experiments with promising results, and the physical vapor deposition technology that is required for the thin film evaporation step has been demonstrated successfully in space. The final choice of the foil production technology requires a deeper analysis of the overall production system, since both techniques have their pros and cons regarding the production efficiency. Now, with the sunshade screen produced, a structure is also required. And as you can see on the next slide, there are two metal printing processes that can be applied in space. The first one is ultrasonic additive manufacturing, where thin foil elements are joined in a solid state welding process that is induced by ultrasonic vibrations. And the second one is electron beam freeform fabrication, where a wire is melted in an electron beam and then deposited onto a substrate. Electron beam freeform fabrication is a process with a rather low resolution, but with a high production rate and a relatively low process complexity. So this technology could be used for the production of rather bulky parts, such as trusses and joints of the Sunshade structure. And ultrasonic additive manufacturing would be used if more detailed parts are required, or, for example, if the Sunshade screen needs to be attached to the structure, or to patch some holes in the Sunshade screen due to the foil joining nature of the technology. Both processes were developed as prototype in a space-like environment. They have a technology readiness level of up to 5 and are basically waiting for a demonstration in space. Now the next slide deals with robotic operations in space. Of course, the Sunshade production operations will be huge and should therefore rely on automated operations. And much has happened in the last few years in the field of robotic operations in space. Most prominently, the Spider Fab concept has been created for the manufacturing and assembly of large reflectors and antennae in space. And the technologies required for this system have been matured and will be demonstrated by NASA on the 2 OSIM satellites in the next years. The first one will assemble an antenna array from several smaller elements and will extrude a carbon composite beam and attach it to the structure. And the second one will go further by extruding a whole solar array or 2 solar arrays and will attach them for further use. So as you can see, the many developments and the money spent for the demonstration missions are evidence of the paradigm shift towards robotic in-space manufacturing and assembly, and a high operational experience for these topics can be expected in the near future. Of course, all these operations need to be powered. So we did take a look into solar cell production on the moon. As you can see on this slide, the huge efforts for Sunshade production are huge, as I said, and therefore it would be an advantage if the power generation equipment could also be manufactured from in situ material in order to reduce the mass that needs to be transported from the Earth. And with the naturally high amounts of silicon available on the moon, silicon solar cells could be manufactured from lunar regolith feedstock. Silicon solar cells have a lower efficiency than the highest grade solar cells available on the Earth or the ones to come in the near future. But they have a high reliability in space with much operational experience and a high lifetime in the space environment. The solar cell concept on the right has been developed in a NASA-funded study. And here the cell layers would be evaporated onto a melted regolith glass substrate, also by physical vapor deposition. It was estimated that a solar cell with a thickness of 20 micrometers and an areal mass of 50 grams per square meter would have a maximum efficiency of about 10%. In laboratory experiments to produce these solar cells, there was no light energy conversion demonstrated yet, so the proof of concept has not been successfully reached. So this is something that must be pursued more actively, as it would reduce the mass to be launched from Earth significantly and could help the ramp up of the Sunshade production industry significantly. Now, with the most critical manufacturing technologies reviewed, 2 Sunshade design concepts have been analyzed further. The first one is an aluminium sunshade, a very simple design consisting of an aluminium support structure and a textured aluminium foil of 10 micrometer thickness. This sunshade would have an areal density of about 43 grams per square meter, which would mean a total mass of 73 million tons. The second one is the photovoltaic sunshade that Ross already mentioned. It is basically the same core structure, but here the aluminum foil is covered with solar cells. And the power generated by these solar cells can then be transmitted by a wireless power transmission to the sunshade production facilities for producing new sunshade, and by that initiate and support the ramp up of the production capabilities exponentially. Wireless power transmission systems have or are studied more and more in connection with solar power satellites, with increasing interest by governments and private companies. So as most of the other technologies involved in these sunshade designs, it has its own economic drive with many secondary use cases. Of course, the photovoltaic sunshade would be much heavier than the aluminum sunshade, with 334 grams per square meter areal density and a total mass of 286 million tons. But as I said, this also already includes the power generation system that would have to be added to the mass of the aluminum sunshade if we talk about the total system mass. Also, the total masses of the sunshades itself are relatively high compared to estimations in previous studies, but they are sunshade concepts that could be produced with a rather low complexity and with technologies that are available soon and with technologies that would have further use. The concepts shown here are definitely not optimal. This is a rough estimation, and all the systems involved in the sunshade production, not only the product, the manufacturing technologies I presented here, must be quantified in more detail. So our next goal at the Institute of Space Systems is to create a digital twin of the total system of the International Planetary Sunshade System that will then be used for optimization studies. And one step in this direction was made by my student colleague Tarshan Maheswaran, who dealt with the question of how to bring these millions or hundreds of millions of tons of material from the moon to the SEL1. So I'll hand now over to you, Tarshan.
So hi, everyone. Great to see that so many people are interested in such a challenging project. So I'm Tarshan Maheswaran, also aerospace student at the University of Stuttgart. And in collaboration with Sebastian's work, we developed a roadmap for international planetary sunshade concept. And especially in my master thesis, I was focusing on the logistical aspects for the IPSS concept at the Sun-Earth Lagrange point 1. So I worked on first estimations for a sustainable lunar launch system and on the trajectory design to build up a logistical network between Earth, Moon, and SEL1. So the mentioned high mass requirements for an IPSS system also call for new launch systems. Therefore, I was focusing on an electromagnetic launcher, a coil gun. So in my thesis, I worked on a first concept to use the coil gun to transport the lunar raw material, which is required for the construction of the whole sunshade concept. So initially, raw material will be transported by the coil gun to a lunar cargo hub at the Earth-Moon Lagrange point 2. So, and then just in sequence, it will be transported to SEL1 by space tugs powered by solar sails. So the coil gun is planned to be located in at the lunar south pole in order to take advantage of lunar conditions, form synergies with future exploration missions, and at the same time enable communication with the EML2 cargo hub. So the schematic illustration shows the setup of a coil gun concept, which consists of a series of coil guns in the Shackleton crater. So depending on the design of the sunshade, so if we take the minimum mass or the photovoltaic sunshades, 12 to 46 coil guns can move the incredible mass of 74 up to 268 megatons of raw material to EML2. So compared to the capacity of the Starship with 100 megatons, 100 tons per launch, we would need a lot of starships, as Ross already mentioned at the beginning. So the coil gun is the more efficient and sustainable launch concept. So the whole overall power supply is planned to be provided by lunar silicon solar cells with a lower efficiency than the current terrestrial solar cells have. But by the in situ resource utilization, we can avoid to bring them up from Earth. So the first estimations indicate that the required energy supply is in the range of terrestrial solar park capacities. So it is comparable to the Butler Solar Park, currently the biggest on Earth, but that one was completely set up in the desert in only 5 years. So we're able to master that challenge, and coil gun can be completely be supplied by solar energy. So the first estimations for the mass requirement for the coil gun indicate that depending on the Sunshade concept, 4.2 to 16.4 kilotons of material is required for the overall coil gun system, which is quite less compared to the performance capacity of the coil gun system. So the first estimations of the mass and also of the costs for the construction of the concept shows that the concept is feasible and the high mass rates can be achieved, which are necessary to build up the whole Sunshade concept. So the coil gun concept or the coil gun itself is a key technology for the Sunshade. And so future work is planned to design the concept in more detail and to incorporate superconducting materials to increase the efficiency.
Thank you, Tashan. So this concludes the presentation. I hope we've sort of conveyed the opportunity to provide some cooling for a future climate catastrophe from space, and how that is basically enabled by scaling up existing plans to a new level of intensity in order to use the industrial capacity that we are seeking to build and the resources of space to save our biosphere and to benefit all of humanity on Earth. I'm going to stop the recording now and we'll proceed to open discussion.